Okay, let's start. So in our last class, give me 1 second. Let me take this one. Okay. Okay, here we go. So in our last class, we mentioned the KNN. Let me have a very quick review. Again, KNN is to classify X by the majority class label of its K nearest neighbor from the training data. So we have shown the example here. Then we continue the example that I did not finish in the last lecture. So here is something about image KNN classification in image processing. So here, first of all, we try to smooth the pixels so that we get the mean of its adjacent pixels first, based on RGB. Second, we had an example here, so we try to classify the things terrain here to be 4 parts: buildings, parking lots, trees, and grasses, and streets. And then we do. And let me have a check of the training data first. So, okay, so the training data here are just the row and column information, and then the corresponding classes. In other words, it tells you, hey, what is the row X, what is X and Y, and then what is the corresponding label based on RGB. Again, be careful, based on RGB. And then wait a second. And then it asks you, hey, how about the things? Okay, now let's go to our lecture 7, the last example. Okay, let me run those cells and meanwhile to have a review. So otherwise, those things, it will show you error because something not defined. For example, if you run it here, it will probably show you error. Yeah, because MP is not even defined because I made things here. Okay, so first of all, we read the original image here. Here's how we read it, and here we have a look at the data. Let me open it. Let me say images. Okay, wait, sorry. I do need to run it again, otherwise it will be wrong. So let me just run it. Okay, so here's the original picture. It will show you the original picture. Yeah, here we go. A bit slow. Okay, yeah, here we go. So original picture, and then we should create something called image CSV. And indeed, you can verify the time. It is the one newly created. I can delete the old one, doesn't really matter. And then if we have a look at it, and we can see that it doesn't have the row column information. So for example, this is this is a cell B1. That means X is 2. Be careful. These B's columns are X and Y is 1, like this one, you can see. And the corresponding RGB of this cell is 179, 180, and 164. And then of course, later we will recode it to be the average, of the adjacent here 6 cells or 6 pixels in total. Be careful, this is indeed a tensor. Why? Because it has IJK, okay, 3 dimensions. And then the second, excuse me, in the second step, we recode the image tensor by using the mean of the adjacent pixels. Sorry, wrong spell. Pixels, if it exists, of course. And then what we did is here for each column, each row, what we do is we consider all its possible pixels, and then we do have a condition, which is if it is greater than or equal to 0 or less than or equal to the shape -1. Why? Because if it does not satisfy this condition, row or column, that means the corresponding adjacent pixel does not exist. So for example, consider on the first row, so that it has only 6, right? The top 3 are nothing. I mean, there's no adjacent pixels, so it won't count like this way. And finally, we write everything in a matrix called image recoded. Let me run it again. Okay. Looks it's done. Recode. Okay, here we go. It's done. So this is the image recoded. I believe in the last lecture I've already showed what does it look like, but really nothing there. The only difference between the original image.csv is that it shows, calculate the mean to smooth the data. And the third, we need to load the training data. Why? Because again, remember the training data, I can close this one. The training data just now we showed, it shows you the row, column, and also the classes, right? So however, what we need is I need to read this row and column information and put this row column information into our matrix. Sorry, I should call tensor. And hence I can get the corresponding RGB for the ith data. And this ith data is our real training data. Again, because the distance is based on RGB. And how many training data we have? We have how many? From 2 to what is the number? What's so many? Okay, 2 to 257, and hence we have 256 data, 2 to the power of 8. So we have totally 256 training data, and hence that's the same. Okay, now the fourth step, what do we need to do is need to do the classification and plot the decision region. Where it is. Okay, here we go. So we will first okay, let me just do it. So we'll first let me see here. I have the X string here. Okay, so here I need to make a mesh grid first. mp.line space. Let's say because I know the pixels, the row and the column begins with 0, and then the maximum is the maximum. I have the image. Let me see. My image definition is small or big image. Let me see. Is it where's my image definition? Sorry. Where it is? Here it is. Image is small. Okay. Is image let's say dot shape 1. Why 1? Because columns are the axis. -1 image dot shape 1. Let me see here. Yes. So this meaning is that the number of the grid is from 0 to the maximum index, right? And then how many you want to generate? It is the total number. In other words, for each pixel, I will have a point so that I can have, like enumerate all the cases. Length space 0 image dot shape 0 dot -1, and then image dot shape 0 for the same thing for y, and then I will have xy equal to mp dot mesh grid xy. Okay, in this case, I've built a mesh grid, and then I need a boundary. Bound. Let me call it, let's say decision region. Or let's say dr color. Let me call it just dr color. Simple. Equals to listed map. And then what are the 3 colors? Every time I cannot remember. Rose brown, light, steel blue. How many? Oh, okay, let me do 2 by 2. Rose brown, light, steel blue. And the other 2 are let me see, pale green and orange. Oops. And orange. So here we have this one, and now when you create a figure, you go to plot.figure, and then what we need to do is, so what we want to do is, we will first show the original picture, and then we want to train the KNN for k equals to 1, 5, and 10, and hence I need to create a subplot, and in which the first one, the 0th subplot is actually the original image. Okay, so AX equal to figure dot add subplots. Plot or plots, every time I cannot remember. Give me 1 second. Okay, subplot. And then I'm gonna do 2, 2, 1. Okay, now I can plot the original image. Image show image show, I believe. Image. So AX dot set title original image. ELT dot show. So let's have a look. Here we go. Okay, so this is the original image. Good. Now we need to do the KNN, right? And then we need to have the subplots. So first of all, make it I equal to 2. This is going to be the index number, and the K list is going to be 1, 5, 10, because 10, not 6. Because what I want to do is I want to do the KNN based on, K equal to 1, 5, 10. Okay, now for K in K list, what shall we do? We will first of all do the, let's say, KN classification, which is model equal to K nearest neighbor classifier, K neighbors equal to K, N neighbors equal to K, and then model dot fit, and then I have X train, Y train, and then we can do what? So here we've already fit the model. Then we to plot the decision regions. The problem is that for the decision regions, we need to because we already have the mesh grid XY here. So sorry. So what we need to do is we need to make the prediction for the corresponding points, right? And each point is what? A pixel here. So we have decision prediction equal to model dot predict dot predict what? Predict. Okay, here, remember the example here, we need to ravel it. Remember the where it is. Where is my, okay, here we go. Similar thing, when you get to the MP array and the ravel.t, the reason in the last lecture I've already mentioned very carefully, I believe. MP.array dot t, and then I will have let me see, what should we have now? Give me a second. I can simply have let me think about it. Can I directly have X and Y? Oh, no, sorry. X and Y are the coordinates. Sorry, they're not the what? They're not the RGB. So here I have to use the image tensor. So image recoded tensor, and I will have, let's say, column 0. So this means the R dot ravel. And then I will do the same thing for G and B. It's a bit long. Let me just make like this way. Okay. 0, 1. This is green, and this is blue. So now I've already predicted everything for each pixels, and now I need to do what? I need to plot, right? Plot the decision regions. Okay, now what I can do is I can use ax equal to fig dot add a subplot q to I, and now I can just x. Okay, so here is one thing. Let me first show a way which later you will see something very interesting will happen. Okay, let's say I add a subplot, then I'm gonna do the p color mesh. And then I can have x, y are my coordinates, and now I will have dr. Where's my predict? Dr predict, decision region predict, and then I will have what I need to reshape it to x dot shape, because otherwise it will show error. So this is going to be a color, and the C map gonna be the dr color. Wait, why? Oh, I use that dr. Okay, sorry about this. Dr color. Wait. My dr predict is here. This dr predict. Okay, so now I can directly just set up the boundary, and then I can have ax dot set title. Say KNN campus. Let's say campus terrain prediction for K equals to K. Okay, here we go. And then, wait, I need to, let me see. I need to do I plus. Otherwise, that's going to be everything gonna, overlap on the same figure. Okay, here. Wait, what happened? The prediction equal to this one T, and the array from 1, but the 3 are given. Let me see. Wait. Oh, okay, here we go. That's the reason why. Let me see parentheses. Yes. I probably should put this one off first. Anyway, let's wait a little bit. Is it still running? Let me see. Run it. Okay. Give it a little time, and you will see something very interesting. Okay. Look like my computer is slow, huh? But indeed, it takes some time because the pixels are pretty big. Okay. Why there's only one figure? Invalid. light steel, sorry, light steel blue. Is it light steel blue? Let me see. Light steel blue. Okay. What did I do? That's so slow. Okay. Sorry about it. Let me rerun it. It's just pretty slow. Let me make sure nothing's wrong. Rosy brown, orange, and then okay, and then here. Okay. Hope everything's correct. Maybe I can just save some time. I can just like this way. Okay, so remember here, I actually did not include this line on purpose, which is ax.image show. People may question that, hey, here you're gonna just add a subplot, right? Why do we have to show the original image in each subplot? Because use a p-color mesh, who cares about the original image? Since here I do x, y equals, for each pixel, I will generate a point. In other words, this xy equal to n mesh grid dot xy gonna generate a mesh for the whole plane, right? So why do I need to show the original image? I can just use a p-color mesh to color it. Everything's done, right? Okay, so reason is this. Okay, here we go. Look at this. Did you see some inter some interesting things? So here I kept all those kind of axes on purpose. So if you check it, you will see actually this is a mirror. So okay, sorry. Can you see my okay? So here I believe I have the point. My mouse is here. So wait, what happened here? There's something wrong with let me see. Looks like there's something wrong with the zoom. Give me 1 second. Okay, yeah, here's my mouse, but here why cannot see my mouse? Wait 1 minute. Looks like yeah, it is probably the problem of Zoom. Okay, sorry about it. Here, yes, here I can see, but why here I cannot see my mouse? Anyway, so but here if you have a look at the pictures, let me try to make it this way. Just I don't know why it looks like Zoom done. Let me show my mouse. Okay, so I'm talking about here first, original image. If you have a look, let's say this image for which k equals to 5. And what you're gonna see is actually in the y direction, it is a mirror, meaning that look at here. So my my y this one is from 0 to large, right? And look at this picture. It's from 0 to large in this direction. In other words, if you check it carefully, let's say, for example, I just find randomly choose a building. Let's say you can see this part of the building, right? And then in this picture, the building's here. You see it? And then next to it is kind of like a bigger building and a grass. And you see, here's a bigger building and grass. You see what I mean? So why there's a mirror? The reason is because here, because I have, the 0 is here, large y is increasing from this to this direction, but here 0 is here to this direction. This is something kind of like an image show versus pie plot. It's something different. And I guess the reason because different people work on this library and hence cause some differences here. That's the reason why I need to add a command here, which is image show, because once I tell it ax.image show image. Once I tell this one, then Python will know that, okay, I will run the coordinate with the image show. So it won't make a mirror here. Let's just run it. Okay, let me run it again. Then after adding this, code, this line, you will see that. Let me show the line number. Sorry, I don't know why the non view line number. Okay, so then it will really show you the correct image. I won't make such a mirror anymore. Okay, so since this one's a bit slow, let me directly start from the slides here. So indeed, you can see here's k equal to 1 equal to 5 equals to 10. You can see actually using such a simple, super simple classifier, the result is pretty good actually. You can see, for example, here are the buildings, and this is all the buildings. And then here are also buildings, and this blue color are what? Light blue color are the parking lots. And this green color is those kind of grass something. And then the bad point, however, is what? The yellow color part, which is the parking part. Let me see. Sorry, yellow color part is a street. However, to be honest, even if you oh sorry, let me here we're done. So even if you let me use it like by my eyes to see it, it's not that easy. You know what I mean? Because somewhat in terms of the color, especially, you can see that the color here, the street, here's the parking lot, they are the same. So if you really want to run something like you just want to differentiate the street versus the parking lot, what you should do is not to only use the color. What you should do is actually use the color plus distance. In other words, say consider this point. This point around it, there suppose I have some training data around it. So I know this is a parking lot. And then consider this one. This one is actually far from the parking lot, although the color is similar. But if I have some points nearby, labeled training data labeled as street, then I'm gonna know it's street. In other words, your training data should not be the tensor of the location versus only including RGB. You should consider the coordinate XY as well. So this is one solution. And another thing is, if we have time later, I'm going to show you an example, which is basically use the KNN, also color-based. An interesting thing is this. Suppose I have a camera. So this is a parking lot. A camera, look at the camera parking lot. Suppose I know, for example, so I have totally 100 spaces for cars, right? I can actually use the camera and use the machine learning algorithms to tell people, say, how many spaces are left. So the idea is pretty simple that I can use RGB. I know what should the color be for my sorry, let me put yeah, what should the color be for my original parking lots? Let's consider here. And now I can see, suppose the color is no longer this. Say, for example, here's a car because another color, blocked. Then I know here one car is blocked. And then I just need to count like how many, those kind of things are there. And hence I can calculate how many spaces are occupied, how many are left. So this is a very interesting project. If you are interested, you can run it. Let's see if we have time, we can run it later when we finish all the classifiers. Okay, so this is everything about KNN. Again, KNN is really very, very powerful, and it's super fast and simple. And there are some theoretical results, kind of like objective rotation rescaling something. If you're interested, you can just go. Sorry, this is not where it is. Lecture 7, right? You can go to lecture 7, and we have some theoretical results here if you're interested. Okay, but here I don't want to spend too much time on theoretical results. And of course, have a good habit, you can write it as a class. So here, because basically nothing, just, based on the code here, for each cell, you can make it to be a function and make the whole thing to be a class. So I'm not going to spend the time here. You can just read the code by yourself if you're interested. Okay, so this is everything about the KNN in our class. The next classifier I'm going to introduce is naive Bayes. Both KNN and the naive Bayes, they are super, super simple and super, super fast. And they are widely used in our lives simply because their accuracy versus their computation cost is worth it. So first of all, we need to have a quick review of the naive, no naive, sorry, just the Bayes formula, because naive Bayes is based on the Bayes formula. And then I will introduce why do we need to add the term naive? What does the naive mean here? Okay, so first of all, recall Bayes formula for events A and B. We have probability A given B equals to PAB over PB, and which is, you just write the conditional probability again, which is this one, PB given A times PA over PB. People may say, hey, what's the point of it? I mean, looks like nothing, right? I want to calculate A given B. What we did was just exchange the order to make it to be B given A. In philosophy, there's a big point, actually. So first of all, this PA given B is called posterior. This B given A is a likelihood. PA is a prior, and PB is a support. Be careful as B is given. So this PB is a constant. And later we'll see this PB is ignored because it's just a constant. Who cares? When we do optimization, the constant, it doesn't matter, And then PA given B means I saw B. Now I want to predict something which, which I didn't know. But PB given A means based on the thing I see. Now, what if I want to see the past, which is the thing I'm interested in now? That thing is given, and then the probability of the B. So this is something kind of like the posterior equals to the likelihood times prior. I should say this, the posterior is proportional to, let me use the term proportional to, because PB again, is a constant. And we of course assume PB is greater than 0, otherwise, it's meaningless and it's positive. So we can just ignore it. It's proportional to the likelihood times prior. I believe in the extension reading here, I showed a philosophy, like a view in terms of philosophy, how to understand the Bayes formula. And I think it's here. It's really no, it's probably somewhere here. It's really very important. Okay, but here we're gonna just simply apply it, and then the chain rule of conditional probability is this. Suppose we have PA1 till PAP, so that I have, first of all, I can take the first one out and consider the other thing to be, the rest, which is I have PA times PA2, wait, PA1 till PAP. And then I can take the PA1 out times PA2 to A3 till AP given A1. Similarly, in this part, I can put the A2 event inside, and then this will be PA given, PA2 given, okay, let me use the probability. Probability A2 given probability A1 times, then what is left is probability A3, A4 till AP given A1 and A2. See here. And then we can continue until what? Until the last step gonna be like here. Until the last step are gonna be finally only one AP, and everything's given A1, A2, A3 until AP minus 1. And mathematically, we can just write in this way. We take the PA1 out and then make a production from J equal to 2 to P. And then here we go. PJ and given P1, P2, PJ minus 1. So this is equivalent to this. Okay, so this is a chain of conditional probability. And then what's the point of this? Because we can use the chain of conditional probability to calculate this one. And then the term naive is actually here. We use a very naive assumption to greatly simplify this production. Let's see. Okay, so first of all, let me define the Bayes classifier. Again, be careful here, there's no term naive. It's the Bayes classifier. We consider a classification problem in which the features, so sometimes features are also called covariates. It doesn't matter, just different terms are denoted by a random variable x equal to rp. So p dimensional has p features, or you can say p coordinates, and a given label. Again, we use the same notation system, which is, totally has m classes. And then let this one be the ith training data. The Bayes classifier is simply a classification method to predict the label by the most seen label with the same, be careful, with the same coordinate. So in the training data, mathematically, we can write it in this way. So the label of BC means Bayes classifier equal to argmax of P, x equal to y, y equal to y, x equal to x. So which one should you choose? You should choose the y, which gets the maximum of this one. So let's see an example, because if it's the first time for you to see Bayes classifier, you may get a bit kind of abstract by the mathematical notations. So say I want to predict a person's gender based on his or her height and weight. So I use -1 to be female, +1 to be male. Where so the training data are in this way. So the first one is the height, the second one is data, the second one is weight, the third one is the gender, which is the gender of the label. Okay, and here height is in terms of the centimeters. For those of you who are not familiar with centimeter, say 1 inch, I believe, is 2.54 centimeter. The reason I use centimeter in terms instead of using inches is because it's always kind of like 5 feet. Let's say 5 feet. Let's say 10 inches. It's not kind of like easy to show it in the data here. So I'd rather make it converted to BCM centimeter. It will be easier. So let's say here I have 165, 130, -1, and the same data again. 1 -1 means female. And this is let me just use something to underline it. Okay, so this is a female. This is this is a female. This is a female, and the rest are male. Okay, so what does naive bias mean? Sorry. So now suppose I ask you this question. I ask you, hey, now let me give you a color. Well, let me give you a data. There's a person whose height is 165, which is about 5'4", I guess. The height is a 5'5", maybe 5'4", 5'5", the height. And then the weight is 130 pounds. Question, is the person male or female based on the training data? So we can see, okay, we do have 3 people in the training data. 1, 2, let me just box it. Let me use another color, let's say red color. Okay, so these are 3 people, see it? The height and weight are 164, 130, right? But among these 3 people who have exactly 165, 130, 2 of them are female, 1 is male. Then I'm gonna classify the person to be female. So that's a naive Bayes classifier meaning that I need to find, in the training data, I find the data with exactly the same X. Here, for example, exactly the height weight must be 165, 130. And then I will check the label. Which label, is the most common, the most seen label in my training data. So I'm going to classify the target data to be that class. That's it. Simple, direct, nice, right? But there's a big issue. You know why? Wait. Before introducing the issue, let me first introduce some mathematical notations. This thing I cannot avoid. I do need to introduce because we use many similar notation systems. Otherwise, you will get confused over the notations later. Okay, so using this idea, formally we estimated the probability of event x given x x equal to x, y equal to y by this. So this means this delta function is the binary indicator function. Indicator function means here, so for this very small area, is this condition satisfied? If it's satisfied, then the delta of this one equal to 1. If it's not satisfied, it equals to 0. So delta is such a binary indicator function. So now let's see what that means. So the condition here is xi equal to x, yi equal to y. In other words, it asks you, so remember, this is vector xi, okay, be careful. Vector xi means the i's training data. In other words, I'm asking you, hey, whether the i's training data exactly equal to x, and meanwhile, the label exactly equal to y, where this x and y are given, you can consider it like for example, test data or target data, whatever. Are they exactly equal? If they're exactly equal, okay, that means the delta, this thing equal to 1. If one of them or 2 of them are not satisfied, then it's 0. That's it. In other words, here, what I'm doing is, in the training data, I calculate totally how many data satisfy the condition xi equal to x and y equal to y. And n is my total training data. And hence, how many occurrence over the total observed data means what? The chance. So we use this one to estimate the probability of x equal to x and y equal to y. But be careful that we are more interested in what? We are more interested in this, which is the posterior, right? So why do we need to care this one first? Because by Bayes formula, we can calculate, actually here's not even Bayes formula. Here just conditional probability, very basic things. So this can be calculated of A and B divided by probability of B. And here's the thing. And this is the thing we just introduced here. And using the same binary indicator function delta, we can estimate P x equal to x to be this way. And that's it should be, sorry, let me write something. Zoom, okay. So technically it should be this way. This one divide by n. And this one also divided by n, because again, how to estimate the probability that x equal to x. Simple. I see how many times x exists and totally how many observations done. So both gonna have divided by n. They canceled, and that's why here, you don't have these two. So let me give you an example. Let's say here, question, what is the probability x equal to this x? Simple, I count. 1, 2, 3, 4, 5, 6, totally 6 data. And then three of them, which is the first three, let me hear. 3 of them have exactly the same data, which is 165 and 130 with the target data. And hence the probability that x equal to this specific x equal to 50%, which means equal to 3/6. Isn't it super simple, right? So the second page, I mean, this is exactly the meaning here. And this looks like pretty kind of abstract, but it's just a mathematical notation. So this is the point. Okay, now we will use the maximum estimated posterior probability to be the label. So I'm going to calculate this one for y equal to 1, y equal to 2 until y equal to m, because y, remember, here's my notation. Y is a total has m classes. And then, so I will have m this data, right? And then I'm going to see which data is the biggest, has the biggest posterior. So then I'm going to say, oh, okay, I'm going to classify this number, this specific x data to be that label. So that's the meaning. So this is the meaning of most seen label with the feature, or you can say with the covariate x. So that's the thing. By the way, one thing I want to mention that for a given x equal to x, and the base is actually equivalent to the KNN with k equal to n. Why? Because the meaning is that I'm going to consider all the data. You see what I mean? And hence k equal to n, all the data. Okay. However, there's looks everything so nice, so easy, but in practice, there's a big problem. The problem is here. So I need to find exactly given x equal to x. But what does x equal to x mean? X equal to x, because x is a vector. So here we go. Let me just write something here. X is a vector, right? So x equal to, I mean, the vector x equal to the small x1, x2 until xp, because I consider two p features. And by the way, the big and the small, the big one means it's a random variable. So that's something that I don't know. Small one means observation. I've already seen it, a realization. Okay. So I require this line, give me a line. Okay, I require this. So, and my notations are this. This means what? This means, okay, I do require big x1 equal to small x1, big x2 equal to small x2, until big xp equal to small xp. Hey guys, think about it, how difficult it is. You cannot say almost, you need all of them simultaneously equal. You see what I mean? What if p is a big number? And then what is the chance for you to get among your training data everything exactly the same? It's very difficult, trust me. And finally, if your p is really big, what you're going to have is this. You're going to have delta xi equal to x. Again, be careful. Here are the vectors, okay? The vectors, not, I mean, this xi is not this xi. This xi is just a scalar. But this xi, all these are vectors. Meaning that all, I need to find in the training data. So here xi is the training data. This x is the vector of the given target data. I need to find like among all my training data, how many training data, or each x, xij exactly equal to my training data, my target data xj. The chance is gonna be almost zero. Trust me. Sorry, this zero should be a scalar. It should not be a bold zero, because bold zero means vector. It should be a scalar zero. The chance is going to almost be zero. And then if the chance is zero, look at this. Here, I have something in my denominator. Denominator zero means what? That means it's invalid. I cannot calculate it. It doesn't make sense. Or a more like practical or intuitive example, for example, I want to predict data. I consider the following 7 features: height, weight, age, nationality, occupation, parents' height, parents' weight, something like this. And then let's say I get 1,000 random sample from people all over the world. Think about it. I only have 1,000 data. What do you think? How much chance do I have if, say, I give you a target data, let's say height, let's say 165, 130, age, let's say 20, nationality, let's say US, occupation, let's say professor, parents' height, let's say 166, or parents' weight, let's say 135, something like that. Of course, I just randomly make the data. What's the chance you think you can find exactly everything exactly the same? Your chance is almost zero. You know what I mean? You cannot get this. And hence those this naive Bayes looks super simple, super like rational, but it's not practical. In the real world, we cannot really use it to calculate. So what's the point? We have this theory. Okay, and hence we need to have, have something called naive Bayes. But what does naive mean? Why we call it naive, right? Okay, here we go. Now, let me show you a mathematical form. Then it's going to be better. So first of all, because the key is here, I need to calculate. Sorry, where it's here. I need to calculate this, and hence I need the numerator, right? Let's temporarily ignore the denominator. Let's consider the numerator. Okay, so this one equal to this, the numerator over the denominator. While we mentioned the things x equal to x, this x is given. So it doesn't matter because no matter what, this is a observed data. I mean, I've already seen it, so I don't need to worry about it. So this is a proportional. This notation means proportional to the numerator. So I only need to focus on the numerator. Then the numerator, as we mentioned, you need to find exactly x1 equal to x, x2 equal to x2, xp equal to xp plus the label must be the same again. Okay. Then by the chain rule of conditional probability that, here we just mentioned, you can write this one to be this form. And then you see the difficulty part is here. You need to have so many conditions given y equal to y, x1 equal to x1, blah, blah, until xj equal to xj minus 1, xj minus 1 equal to big xj minus 1 equal to small xj minus 1. Too many conditions, too strict that I cannot easily satisfy. So the naive Bayes assumption is that given the sample label, all the p features are mutually independent. Still remember the point. Let me write something of the independence. So consider two events A and B. Okay, I have P A given B equals to equals to equal to PA if A and B are independent, right? So now think about it. Suppose that's the definition, okay? Suppose I have all xi's are independent. All of them are mutually independent. What's going to happen? What's going to happen is that, let me give me a box zoom here. Okay, let me use another color, let's say yellow color. What's going to happen is that all of these will be gone. Why? Exactly the same reason here. Be careful. X's are mutually independent, not y. Okay, y is still dependent. You still need a y. Okay, so think about this. Similar, right? A given B equal to PA if A and B are independent. Here, I'm interested in xj, and xj is mutually independent with all other x. I mean, x1 to xp. Of course, it's not independent of itself. I mean, or other. Okay, other things. So of course it's independent with any of them. So the whole this box can be gone. And hence we have this. Such a big, item, complex item becomes so simple. And indeed, later you will see, we will consider 3 cases to calculate it. And no matter which case, it's extremely fast to calculate. So this is the naive Bayes assumption. And hence, you just substitute this one here, we get this. This equal to I should write proportional instead of equal to. I should write it to be proportional to this times this, given the naive Bayes assumption. Okay, now you can see compare the naive Bayes classification versus the formal Bayes classification. The only difference is that in the naive Bayes thing, we added this naive Bayes assumption, right? Then why do we call it naive? Simply because this assumption is pretty naive. Because in your real life, this is not always true. And actually, in many cases, this is wrong. Because think about it: height, weight. I mean, they're dependent, right? Usually, I mean, on average, if a person is taller, then usually the person gonna be heavier as well. Again, on average, and vice versa. So it's not completely independent. And hence, this is pretty naive. So we call it naive Bayes assumption. How a naive Bayes classifier and the corresponding assumption is naive Bayes assumption. However, be careful. that since later you will see, since the computation is extremely simple, and hence, even if we know sometimes say, I know that the naive Bayes assumption may not be properly working in my example, it's still worth to try it. Why? Because it's possible that even if it doesn't work, the computational result is still very, very good. Why? Because my cost is super fast. I mean, it's actually linear. The speed is actually O maximum of n to p. It's a linear speed. You will see it later. So here we plug in, this assumption into our classifier, which is this one. Then we will have this. Okay, so we have this one, and then this one is proportional to here to when we say arg, it's equal the same thing because why? When we do optimization, if there is a positive, integer, which is nothing but the denominator here. So this is a positive integer. We assume it's not zero, so it doesn't matter, Okay, so now this equal to this, and then by the chain rule, we write it like this way, right? And then finally, by the naive assumption. So sorry, what I meant here. Sorry. From this line to this line, we already applied the naive Bayes assumption here, and then we just take the logarithm because we're in maximum, so logarithm of maximum still still the same thing. Still arg. So we get this. So the difference that I don't have the production anymore. Everything's gonna be summation. And later you will see we assume those assumptions. We have exponential, and by log, exponential directly become a kind of coefficient before log. And then here, this py times this becomes plus. So I can have the whole thing is argmax of this thing. Okay. Now, first of all, using the idea that we just mentioned, P y equal to y is what? Is this. So this means, okay, among all your data, how many, for each label, for each given y, how many training data have this label? And then among your total number of training data. So I can use this one to estimate the frequency or the occurrence chance of a label y. So for example, here, let's go back to this baby example. So I have 1, 2, 3, 3 are female, 3 are male. So I ask you, hey, what is the probability that y equal to -1? In other words, the person is female. Okay, among 6, 3 of them are female. So it's a 50%. And of course, male is another 50%. So this is the meaning. It's super simple. And now the problem is how to calculate this green part, right? Okay, because the green part basically it depends on the space of my training, the data X given y, given the label y. So we will discuss 3 cases: continuous features, categorical features, and counting features corresponding to Gaussian naive Bayes, categorical naive Bayes, and the multinomial naive Bayes correspondingly. And there's a detailed document for I believe this, SK library, SK learn. If you're interested, you can just read it. Okay, first let's have a look at Gaussian naive Bayes here. Drink some water, sorry. Okay, so now suppose the space of each feature J is R. R means a real number. So the Gaussian in the Gaussian naive Bayes, because each feature is is a real number R, so we can use the Gaussian distribution. And people may always ask, so why do you assume Gaussian distribution? Why don't you assume other things? The main reason, if I assume everybody has learned a probability theory, the main reason is because the big number theory, which means if my sample is big enough, I can always use the frequency to estimate the true population probability. And the second is CLT, central limit theory. Central limit theory tells me that whatever distribution you give me, even you can give me a discrete distribution, not a necessary continuous distribution, as long as you make the data minus the mean over the square root of n, over sigma over n. So what that means is this. Let me write it down here. Okay, for any distribution, you give me like x bar minus mu, and then sigma over square root of n. where X is whatever distribution. You can really, if you check my lecture notes, I even do some examples. At that time, I believe I used MATLAB to write a code or something. I forgot. But really, whatever the distribution, this follows normal distribution, standard normal distribution N01. Sorry, this is N01. Sorry about my handwriting. N01. And that's why normal distribution is so powerful. I forgot whom. There's even a very, very famous person, scientist mentioned that normal distribution is the language of the God. So, that's why in many, many examples, even nowadays, like we do, they say diffusion model for those kind of like image data. I don't know whether you're familiar with the diffusion model. So basically you can just, change, a picture from A to B. And then that's how those kind of techniques like now let's ChatGPT and those kind of things, you upload an image and then it will make a very, very small short video for you. Why? Diffusion model. But anyway, we don't have the time to introduce this in this class. So what I want to say, that's the reason why we always assume normal distribution or Gaussian distribution, another name, for those kind of continuous features. And so for given Y, here, so we assume the mean is mu jy and the sigma is, sorry, the variance is sigma jy squared. And hence the PDF is this one. And then the thing is, how would you estimate the mean and the variance, right? Simple, but the simplest statistics. So again, the mu, which is the mean, we're going to use the sample average to estimate it. For sigma, we're going to use the sample variance. And this, again, this delta is the binary indicator. That means whether y equal to y. If yi equal to y is the label of the ith training data. If yi equal to y, then we count this training data. If yi doesn't equal to y, though, we just skip it. So that's the meaning. Super, super simple. Okay, and we are going to do it for all j equal to 1 to p, and also for all y for all the classes. So using this one, I will get for each j and y, I will get the mu jy. And I get the whole distribution. And then I have this, you know what? I can calculate I can calculate this one. Why? Because this is nothing but the PDF of this Gaussian distribution. And then because of the naive Bayes assumption, I simply just multiply everything. And then after log, I just summation everything, then done. So the detail, well, I actually don't have to. But yeah, this is the, let me see where this calculation continuous feature. So here we go. So this is the log form of everything. I get here and I get the log form, and I just need to plug in this one into where? Into this. This is the same as what we calculated, because this py equal to c, this is already given here. And then we just need to plug in this thing, then it's continuous feature. Yeah, we just need to plug in this thing inside, then done. So that's how number six here, plug in this thing, done. So, and then of course for each y, you're gonna have one posterior, and you calculate, oh, which y label has the biggest posterior. Okay, then this test data X is gonna be classified into that class, done. So that's the thing. Okay, now let me just close this one. Let me go back to my slides where we are. Okay, so this is the Gaussian naive Bayes. The good thing is scikit-learn already has everything coded. So, we can directly use it. One thing I do need to mention that people may ask that, hey, you teach machine learning, just teach machine learning, you just purely teach us coding. You can say, okay, here, there's something called a naive Bayes, here's the code done. Why do you need to introduce so many mathematics? The key is that later, if you code more and more, you will know that actually, to be honest, those coding things are very, very simple. The soul of machine learning, of AI, is the mathematics, the algorithm, instead of coding. You know what I mean? There are millions of kind of like video in the world in YouTube. You can search. Somewhat I hate some videos. They just say, okay, today we're going to use naive Bayes. Today I'm going to use KNN. I'm going to use, let's say, logistic regression, do the classification. Oh, looks nice, so simple. But do you really know what is naive Bayes? You don't know it. So I want to introduce some mathematics so that people know how did we get the thing and why we use this thing. So later, in case you have something, you may want to apply different things or create even your own algorithm. So that's the reason why I insist to introduce some mathematics instead of purely coding here. Okay, so here we can let me show an example how to run this Gaussian naive Bayes example. So we basically generate all the numbers and then okay, let me just write it because later we will still need let me see what is that kn. Okay, so let me create a lecture 8. Okay, first of all, we need to import all the things, import I and then p import matplotlib dot pyplot lplp, and then from scikit-learn dot naive Bayes. Come on, come on. Okay, here we go. Import Gaussian naive NB. Okay, so now what you need to do is first to generate the training data. Let's say Gaussian distributed training data, because here we're talking about Gaussian NB. So x1 equal to np dot random dot multivariate. Multivariate normal is because we have x and y 2Ds. Then I need to have my cheating sheet. What are the numbers? 10, 10, 25, 6, 6, 36, and 50. Y1 equal to np dot ones. Let's say, is it 50? Yes, 50. Okay, then I just copy and paste. Okay, now I change to be x2, y2, and x3, y3. And then what are the numbers again? Negative 10, 10, 28, 8, 25. Here, 149. Oh, what? No, 20. Negative 12. Okay, here we go. So now I have all this data. Then what I need to do, I need to first of all have x equal to np dot concatenate x1, x2, x2, x3. X is equal to row, and now similar thing. And let me write y equal to np dot concatenate y1, y2, y3. X is equal to row. Okay, so now I've already had all those data. So what I can do is first of all, let me plot the training data first. So plt dot plot. Then I have x1, 0, x1, column 1, and then red label equal to let's say training data class 1. Okay, now I can just wait. X2, X3, R, G, and B, and then classes 2 and 3. So, oh, that's why I really hate the keyboard. Okay, here we go. So these are the training data, and these parameters are choose. Try to let them, not not to be too close. And then we're gonna have what we're gonna train the naive Bayes Gaussian, right? Train the let's say Gaussian naive Bayes. So model equal to Gaussian model equal to Gaussian naive Bayes, and we will have a model dot fit xy here. No, I don't have x train, y train. So model dot fit xy. So now our retraining, what should we do? We should plot the decision regions. So similarly, x is 1 equal to np dot lane space. And then let's say x 0 dot mean, let's say -5 or -10, whatever. It doesn't matter. These things are really doesn't matter. I forgot what I use in the slides. Dot max dot okay dot max. Let's say +5. Okay. And then let me see how many I generated. 200. 200. And then mash grade. Yep. And then we're gonna do what? We need to predict the y, right? Y predict equal to, again, be careful about the ref model dot predict, and then np dot array dot t. And then here we go. We will have what? We will have x1 dot ravel, x2 dot ravel. Okay, now I have a y predict, and then what I'm gonna do is I need dr, let's say color, decision region color equal to listed. Oh wait, did I load it? I forgot. So I need what? I need from map.lib.color. Color is a color. Colors, okay. Import listed color map equal to, so listed color map. And then the color I remembered light corals, light coral. And then is the light, let me see. Light green, light blue, something. The second one's light green. The third one light blue, okay. Light green, light blue. Okay. Now we can use the P mesh to plot everything. PLT dot P color, not P mesh. P color mesh. And then X1, X, Y predict dot reshape. X1 dot shape. Z map equal to dr color. Okay, here we go. Okay. So this is the decision region of naive Bayes. And indeed, you can see it's even not linear. You see what I mean? Because the boundary is not linear. So this Gaussian naive Bayes, of course, not linear because your PDF is Gaussian function. Gaussian function is highly nonlinear. So that's the same. Be careful again. Gaussian naive Bayes can only be used if all the feature J, all the feature of X are continuous features, okay? And the domains all are. Otherwise, you cannot use a Gaussian naive Bayes. So this is class number 1. Class number 2 is called categorical naive Bayes for categorical features. So what does categorical features mean? It simply means they're all integer. So Z is integer, in the set of integer. MJ means I totally have MJ, the dimension is MJ. So suppose for feature J, it has MJ possibilities. Let's say feature 1 is gender, so it has positive, -1, +1, meaning male and female. Feature 2 is, for example, let's say nationality. For example, okay, suppose we consider, let's say 5 countries. Let's say US, Great Britain, let's say China, Japan, and then one more, Canada. So, the M2 gonna be 5, M1 gonna be 2, So for each feature, it's a categorical. So be careful. You see the difference here is for each feature, the domains are. Here for each feature, the domain is an integer set. Or you can say each feature is kind of like class, a category. So that's the meaning categorical naive Bayes. Okay. So categorical naive Bayes are usually used for those kind of categorical features. Basically, exactly the same idea, which is the number of samples with label Y and it's a feature J in category RJ and divide by the total number of sample with label Y. So this way we can what? We can just estimate the probability that the feature J is of category RJ, JK, sorry. right? So that's the thing. Okay, now formula we can write it in this way. So sometimes, like for me, I prefer to see the mathematical formula. It's going to be more clear. In other words, xj equal to rjk means what? Means of this one. And rjk, the meaning is that, I mean, first of all, for the jth feature, k means the kth category. So that 1 minute, let me check here. Yeah, k means of label k, not kth category. Label k of the, I mean, the jth. Let's say again, let's use a country. Let's say the jth feature, the jth feature is kind of countries, as we mentioned, the US, Canada, Britain, let's say China, Japan, 5. So that your j equal to 2, because we're talking about a second feature. Your k1, I mean j1 is US, j2 is, let's say, Canada, j3 is like from Britain, like this way. And then simply here you just count the thing, label equal to this, and xjk equal to this specific category. Let's say we're talking about let's say a person which is a female and the country is US. So that you're going to only consider, okay, label is a female, and then the country is only US. So that's it. And divide by totally how many US people in the training data are female. So in this case, I can estimate this one. And then the problem is sometimes the numbers could be very kind of like small. It's not like or very big. It's not kind of smooth. To this point, we use the idea of Laplace smoothing, technique. So we add a smooth parameter here, S, and this mj is the total number of the category j. Again, let's say category 2, which is country, so that mj equal to 5 countries, as we mentioned. So this is smooth parameter, but basically nothing. You just add something. The calculation is extremely small, extremely simple. So once we have this one, we get it for xj, and then x equal to this one, and then what we need to do is what? We just need to substitute everything here. Substitute everything here, and then plus this one, done. And then we get, for each one, we get a posterior. Again, we choose the label as the biggest posterior, done. Okay. So if you want, you can code no longer naive Bayes or categorical or the multinomial that we're going to mention next to it. You can actually code it by yourself. You even don't need to use the scikit-learn, because really the calculation is really extremely simple. But here, because I'm lazy, so I'm gonna still code it as the directly use I'm not gonna code it, sorry. I will directly use the scikit-learn to make my life easier. Okay, so here we go. Let me just create something here. Okay, so now let's run I forgot a little bit. Okay. Categorical. So let me still copy and paste everything here. In terms of instead of naive Bayes, I'm gonna have categorical MD. Okay, and all other things I believe the same. So first of all, I actually can copy and paste almost everything here. Okay, first of all, generating the categorical training data. Here you cannot use this. You can use rand int here. And then let me rewrite everything here. Just okay. I need to introduce a little bit of rand int. So rand int, you will have let me see whether it's smart enough to show you. Okay, great. So by the way, just press the shift in the table so that it will show you the hint. So low, high, size, in a type. So be careful, the low is inclusive, high is exclusive. Meaning that, say, suppose I play a die, I want to say, okay, I want to, generate a number from 1 to 6, right? And I want to generate 100 times. Be careful. If you write this way, it's wrong. You will no longer see 6. Why? Because 6 high is exclusive. You know what I mean? In other words, this is going to generate from 1 to 5 instead of 1 to 6. If you don't believe it, let's do it. And then let me print it, x1. You see it? There's no 6 at all. Only 1 to 5. See it? But if you write it to be 1 to 7, then 6 gonna show. Here we go. 6 shows here. Okay. So this is meaning, but it's a random int. It's not a random multivariate normal. It's gonna be random int. So okay, let me see what are my parameters here. 1 to 20, 20 to 40, 10 to 30, and their size is 50. Oh, 50. Okay, so 50 means I need a 50 data. 2 means two-dimensional data. Why? Because I need to show it on X and Y. So, okay, so now I have 1 to 20, 20, 20. Size is 50 and 2. So this is my what? My X1. And then I can just uncomment everything here. Y1, Y2 the same, and let me just copy and paste here. Okay, X2, X3. X2 is right now 20 to 40. And then the last one is 10 to 30, right? Let me see, what is the number? Yeah, 10 to 30. 10 to 30. 52. Okay, and now this is the same, this is the same. So I'm gonna plot the categorical data, but here is no longer a naive Gaussian based, but a categorical MB. And here, remember, we mentioned the Laplace smoothing number. So I can actually add this Laplace smoothing number. Here it is alpha, the alpha. Okay, so by default, the naive smooth is equal to 1. Alpha equal to, I believe, 2. Yes, equal to 2. This alpha is just the Laplace smooth number. Okay, so I have this one, and I can print everything. Let me see. Do I need to change anything? No, I think I can run it. Yeah, let's do it. Uh-oh, great. What is the problem? Size is not defined. Really? How come size not defined? Size shows here. Oh, size equal to, sorry. Okay, and then let me see what predicted negative. How come I have negative data? I should never have negative data. Let me see. Okay, here we go. So for naive bias, be very careful. So sorry for categorical. So scikit-learn, that's actually some problem of scikit-learn. Scikit-learn library enforce all the categorical data to be non-negative. That's something I don't understand, to be honest, because in my personal view, like gender something later, if we introduce support vector machine, we always define it to be -1 and 1 in term instead of 1, 2, or 0, 1. But I mean, it's again scikit-learn, the library, it enforces you to make everything non-negative. And hence you see it here, we already have ones here, and 1 minus 5 equal to what? Equal to 0. So it will have the problem. So to make my life safer, I can just delete all this. So this guarantees that there will be not anything, but the bad point is that you will see the some points on the boundary. Okay, here we go. You can see here, kind of points are on the boundary. Okay, so you may immediately see a big difference. See here, everything's so smooth, it's continuous, right? But here's like block, block, block. Why? Simply because here we have categorical data. By our definition, the categorical data, they must be integer sets. You know what I mean? In other words, by scikit-learn, you must be, categories, let's say 0, 1, 2, 3, 4, 5. You cannot say I belong to category 0.5. No, either 0 or 1. And that's the reason why, it's like looks like blocks. That's the reason. And this is the result of the categorical. So by comparison, again, Gaussian is everything is R. Here is categorical is everything is what? Is categorical. Okay. Now, third thing I want to introduce is very, very powerful, which is called multinomial naive Bayes. This is widely known for those kind of counting features. What is counting feature? By meaning, I want to count a number. But wait 1 minute. Before it, let me first introduce the multinomial in case some of you may not be familiar. I believe everybody has learned the binomial distribution in probability, which is one of the most powerful and useful discrete distributions. And there are tons of theories here. No, I don't have time to introduce, but that's very extremely important in financial, those kind of things. Okay, now the binomial PMF is this. The meaning is that I'm gonna count the number of success, the so-called success. So I only have two cases, success or failure. I'm gonna count the number of success from W independent, identically attributed, distributed, let's say RID trials. And then the probability of success is theta. So the failure probability is 1 minus theta. So the PMF is, so suppose among these W times, I have X times of success. Then how many cases, which is W choose X from W. This is the binomial coefficient, okay? And then this is theta means the probability. So among these X times, I'm successful. Among this theta, C equal to 1 minus theta times, I fail. So this is the probability, PMF. Okay, similarly for multinomial distribution, it's an extension. So binomial, I only have two cases, two outcomes, success or failure. But here I can have many success, let's say outcomes. Let's say I have P outcomes. The reason I use P is because I want to make the notations consistent because we have P features. I have P success, P outcomes. Then I will of course have theta, the summation of all the theta equal to 1, make it to be a PMF, probability mass function. And the PMF of a multinomial distribution with WRID trials are this. And be careful, I coded X to be in this way. This means for each kind of like outcome, how many times. So I have probability X equal to X. This again introduces how many, for this outcome 1, for example, it occurs 2 times, outcome 2 it occurs 3 times, and outcome 3, 4, 5 occurs 0. And total, let's say I do the thing for 5, I make it a trial for 5 times. So it's going to be 5, choose 2, 3, 0, 0, 0. So in general, it's going to be W, choose this. And then similar to here, I will have the probability of theta j to the power of xj. So this is the thing. And people may ask to say, hey, why here you have a Kasi? But the same thing, because here two outcomes. You know why? Because theta plus Kasi must be equal to 1. Similar here, the summation of theta j must equal to 1 because I need to make it guarantee it's a probability mass function. So that's the thing. And then here's the multinomial coefficient, which is this. I guess if there's only 2 items, it's going to be more familiar, which is, let's say 5 choose 3 equal to what? Equal to 10, right? But here, similarly, multinomial coefficient. So this is the multinomial naive Bayes and the multinomial distribution, which is nothing but an extension of binomial distribution. Okay, now let's see, how can we connect the multinomial distribution and the counting feature? So first of all, counting feature means count the numbers of occurrence of a feature. And here we specifically, in this class, we specifically mention like spam email detection. Remember the very first example, I showed a very simple calculation of how we can calculate, we estimate those kind of sensitive words, kind of like bomb. I just remember the word bomb, something like that. Then I'm gonna say, oh, whether it's kind of like terrorist like attack or something, it's gonna worth our attention. The meaning is similar here. Like if we want to detect something, whether a given email is a spam email. So the thing is this, well, multinomial distribution is a natural probability tool for us to fit those kind of counting features. Why? Because we're going to consider, or we are interested in those P counting features, let's say P sensitive words. And then I can use a data, the ith training data, to introduce that this way, equal to xi1, xi2, blah, blah, xip, because we have P such features to denote the number of times of occurrence, of those sensitive data, of these sensitive features or sensitive words in data I. And so assuming we have enough labeled training data, and in the real world, you always have enough, especially for Google. Think about it, how many people in the world are using Gmail, and every day, how many people are gonna, indicate those kind, okay, this email spam, I click, spam. So Google, it is always collecting the data from users. So it has really enough training data. And then for a given data, the probability of occurrence of outcome J can always be estimated as kind of like a constant, and hence we have all those kind of theta this kind of theta, let's say 1j, 2j to theta pj. And then once we have this, and then we can calculate W, which is a summation of everything, then we immediately have a multinomial distribution. No worry, I will give you some examples here. Yeah, here's the first case. Excuse me. So we consider a spam email filtering problem. So suppose we are interested in 5 text features: dollar, selected, link, account, and a win. So basically, I want you to detect something like this. Congratulations, you have been selected to win 500,000. I know now 500,000 maybe not that attractive anymore due to inflation. Now I received a new emails kind of like 2 million. Okay, great. And then click the following link to create an account and then claim your award, something like that. That's why, suppose I'm interested in this where we are in this text features: dollars, selected, link, account, win. Okay. And we have n labeled emails as a training data for m equal to 2. Y equal to 2, the simple spam, not spam. That's it. So we use xi1, i2 until i5 because I have 5 feature data to indicate the number of parents occurrence of these 5 words in training in data I, or you can say in training email I. So I will give you n emails and then for training, and then I will give you a new email. Say the email is X. I'm gonna ask you, hey, is this email spam or not? You know what I mean? So that's the point. And then, as what we mentioned here, this will follow. We can model it to be multi-normally distributed with these features. Immediately, the question is how to estimate these features. So first of all, for W is extremely simple. We can use it to be the total appearance, not appearance of those sensitive words. And the theta j y is the probability that under label y, sensitive sensitive word j shows. Then the problem is how, okay, now I already know how to estimate the W, but how to estimate, theta jy, how would you do it? In the next slide, we will see how can we do it. Okay, again, we use similar things here. So first of all, this follows more formally, this follows multinomial distribution. And then we need to get W and theta j. And we can actually use some similar ideas as we discussed in naive Bayes. So we can estimate the probability of occurrence of outcome J, theta jy, by the training data as follows. Totally, how many occurrences of all features in the sample data with label Y? Let's say totally how many let's say how many spam emails. And then here's among all this, the same label Y, okay, all these spam emails, how many times the feature J, let's say a sensitive word, dollars, occurs. So using this one, I can just estimate the theta jy and for the probability. And then once I have all this theta, height means estimation. Once I have all this theta jy, I can just, and also I have W. The W is going to be the summation of all of them. Here we go. And then I can just plug in everything to the multinomial distribution. And hence I immediately get this conditional probability. You see what I mean? Once I get this conditional probability, isn't it the case? I can use the naive Bayes. I can do everything. Be careful here. Here, actually, we are not even using naive. Till this step, we are actually using Bayes, not naive Bayes. We try to calculate this one, actually. But later, you will see why do we need to use the naive Bayes and how can we, apply it in the multinomial naive Bayes classifier. Let me continue here. Also, we can add some Laplace smooth parameters here, S and P. Here, P means we totally consider P features. Okay, and then we can choose the WI represents the total number of occurrence of all features of data I. And so it is just, okay, I'm going to submit all the features. Let's say for my training data, my training email, if I'm curious or in all those 5 words, I just count totally how many occurrences of these 5 words. And then the W is even stronger, which is for the target data, totally all of them, how many occurrences. That's the thing. I believe I have another example here. Yeah, which is right here. But let me finish the theoretical part here first. So everything can be calculated. Great. Then we can use it to be Bayes estimate, Bayes classifier. And everything looks interesting. Say, hey, you are introducing the naive Bayes here, and you tell me a method that I can use Bayes to calculate. Isn't it ridiculous, right? Don't worry. There's indeed an issue. Because as we mentioned, in order to calculate, it's here, in order to calculate the PMF of the multinomial distribution, I have this, right? Okay, now I've already calculated the theta, estimated the theta. I've already estimated the W. I've already, for a target data, I've already have X1 to XP. I have everything. So what's the problem? The problem is exactly here, this multinomial coefficient. I don't know how many of you still remember, I have to write it, still remember things like this. Let's say M choose K. How would you do it? So M choose K equal to, okay, the formal formula is in this way. M minus K, K factorial. Okay, sorry for my broken handwriting. The formal way is this, but for a real calculation, let's say, for example, let's say phi choose 2. I'm not going to write it in this way. What I'm going to do is this, phi times 4. I will just multiply this for these numbers and then 2 factorial. We're going to calculate it this way, right? Okay. Unfortunately, this trick doesn't work in multinomial. Remember the formula for calculating multinomial? It's here. It's pretty long. And indeed, let's say your P is big, it's gonna kill you, even kill the computer to exactly calculate this number. And hence, again, although this Bayes classified everything from the modeling to calculation, from the modeling, to application to introducing the Laplace smoothing parameters, everything's so nice. It's not practical because you cannot calculate this number. You know what I mean? Now we can play some lazy people's naive dream, which is by the naive assumption. By the naive assumption, what do we have? That all the features are independent, right? In other words, all these, what's called theta, J, Y, they're all independent. And hence, I can simply estimate it to be in this way. Let me give you a box. Give me a box here. I can simply estimate it everything to be in this way. And so you see how easy it is. I directly have theta jy to the power of xj. And then I can completely ignore this binomial, not multinomial coefficient. And you may still argue that, hey, it's not easy to calculate the exponential. No worry, remember what we wrote here, slide number, remember, we have the logarithm, and that's the point. Once I get the logarithm, all multiplication becomes summation, and all exponential becomes nothing but a simple coefficient here. And you see how simple it is. My y and b simply equal to argmax of, I'm going to consider all the labels of 1 to m, categorical, label. 1 to m, this is not a categorical label. Categorical is here. Then I consider all the features, and then it's going to be like this. And where the theta hat jy can be calculated here. And this one, and then W is this one, and W is this one, WI this one. So everything can be calculated. And the time is linear because it's extremely simple. Of course, here I ignore the constant. Why? Because it's here. If you go to slide number 8. So technically, you see what I mean? Here, technically, you need to add a log of this one, right? Log of this one is what? Log of 1 over n plus log of this part, right? But log of 1 over n is a constant. So I can just ignore it. Why? Because I'm calculating argmax. So where it is? So everything's done. That's how I can calculate the multinomial naive Bayes. Some of you may get kind of dizzy. What the hell are we talking about? No worry, let me show you a detailed example. Okay, congratulations, you have been selected to win 500,000, let's say $5 million. Click the following link to create an account and claim your award. Everybody knows, human knows this is a spam. But how to detect it? Automatically use machine learning. So here, use naive Bayes. Again, as we just mentioned in example 821, let's suppose, okay, we consider the 5 features. which is dollars, selected link, account, and win. And then we use xi to xi, xi1 to xi5 to indicate the occurrence of each of them in data I, or you can consider in email I. And the data is right here. Let me show you here. All the data can be downloadable, are downloadable in the Google Drive. Okay, so here are the here are the words. So oh, by the way, what is that? Oh, this is from a previous example. Okay, so dollars. So this one means it occurs one time. Selected means it occurs one time. Be careful, it doesn't have to be occur one time. It can occur several times. Okay, for example, here I can have $2 occurrence. And then link occur one time, account occur one time, win show 0 time, and this email is not a spam. And let me show you a spam email. Spam email like here. Let's say let me see here. Let me make a frozen view. Let me see, freeze panel. Let's freeze top row. Okay. So let me show you a spam email. Spam email, let's say here. Let me show it like here. So it shows dollars one time, shows word selected one time, shows link one time, account one time. It doesn't show win. So maybe you will receive an email say, oh, hey, you just inherit a will, which is $5 million. You're selected to get this will, by a gentleman, blah blah blah, and make some stories to tell the life of the gentleman. And then click the following link, and then to open your account, something, and of course, it's a spam, So again, this column is a label column. Spam is 0. Spam is 1, 0 is not spam. And these are how many times, the frequency. That's why it's called a counting feature. How many times in the data or in the email, in the training email, it shows. For example, this is 171 training email. It shows $2, 1 selected, 0 link, 1 account, 1 win, and it is marked as a marked as a spam data. Okay, now let's go back. Here, excuse me. Because I'm lazy, so I set up the smooth parameter to be s equal to 1. And also because by defaulting scikit alerts s equal to 1. So, okay, now we can use this formula as we just mentioned to calculate the thetas. So for example, let's say theta 1, 0. So y equal to 0 means it's a spam email. It's not a spam email, sorry. J equal to 1 means we only focus on the first feature, which is dollar. So I'm gonna say, okay, among all my training data, how many occurs, which is, I just count the total number of occurrence of the dollars with label y equal to 0. In other words, okay, I'd better just calculate it for one time so that you're gonna see it more clearly. Here for I'm lazy, I'm just gonna use the Excel. Okay, so first of all, I need to count, which is among all label equal to 0, how many occurs. So what I'm gonna do is simple like this. Summation, where it is, sorry. Where it is. Okay, I just write here, equal to summation of, because I sorted by the span, so I just need to, do this. For the dollars, okay, totally among all this equal to 0, span email equal to 0, summation of this one. How many? Okay, so in all non-spam emails, dollars totally occurs 55 times. Okay, now this needs to plus 1. Okay, the second thing is what? The second thing is in all the emails, the total W. What does W mean? Remember it? WI is nothing but the total number. 1 minute. 1 minute. Total number of XI. Total number of occurrence of all features in data I. Okay, and then let me see here. And then here after the summation of I to n. And it must be yi equal to 1. Okay, here we go. So this W is the summation of all those features. In other words, it's going to be a summation of all of them. Be careful, given the label equal to 0. Okay, so these are all of them, this kind of features that I'm interested. Wait. And then don't forget, I have a Laplace, because my total feature is 5, and the Laplace smooth parameter is 1. 1 times 5 is 5, so I need to add a 5. Okay, and hence this theta, what I'm talking about, the theta 10 equal to this. This divided by this. And you can see S 0.221. Okay, so that's how we calculate. Isn't it extremely simple? And you can just write a code. And then correspondingly, you can write for everything. 10, 20, 30, 250, and here 1121. I mean, again, zero, the second label zero means not spam. The second label one means spam. You calculate all of them. Okay, now I've already calculated all the data. Okay, now consider the following target email. Target data, which is you win 1 million, only $100,000. I'm not interested. You win $100,000. Create an account to claim your $100,000. Okay, is it an email? Is it a spam email? So first of all, you need to code it. So because this is this is a text message, you need to code it to be a target X. This X equal to what? How many times dollars occur? 1, 2, 2 times. How many times selected occur? No selected. How many times a link? Is there a link? No link. How many times account and win? Account 1 time. Win is here 1 time. So this target data, if we code it to our system, it's going to be 20011. Okay, question. Is 20011 a spam email? According to based on our training results here. So this is our training data. Is this a spam email? Okay, let's see. So first of all, I already have these things, and then that's what we said. First of all, from the email, we coded the data to be 20011, and then hence xj equal to 4. Why? Because how we calculate W? Summation of everything. 2 plus 0 plus 0 plus 1 plus 1 equal to 4. Second, by the fitted all these things, and also by this formula, which is the MNB multinomial naive Bayes classifier. Then I can just simply calculate the log posterior. Again, be careful. The so-called log posterior means omitting the constant, okay? So I just, very, very simple. You just plug in all the data here to save time. I'm not gonna do it, but basically just, you just plug in all the data to the formula. And then I will calculate for y equal to 0, the number log posterior is negative 1.402. Of course, the log will always be 0 because, from when log x less than 1, log x is negative. And then for y equal to 1, which means spam, similarly, I calculate the log posterior here, and blah, blah, blah. Again, you just plug in all the data here, and then it's going to be this. Which one is bigger? This one. Be careful. When I say bigger, I do not compare the absolute value, okay? I consider just the value. So negative 0.9 is greater than negative 0.4. Hence, what? This is a class. In other words, I say, yes, this is a spam email. Isn't it nice? Of course, I mean, the everything can be calculated by Python, by secondary. You don't have to really do it by yourself. So let's run it here. Let me see where's the thing. Where's my mouse? Okay, so here I'm gonna say first of all, I just copy and paste everything again. This time I don't need this too. I don't need this one. I don't need this one. Okay, from naive Bayes, I'm gonna calculate what? I'm gonna calculate what's called the multinomial MB. Okay. And then wait, I need to import pandas, I realize, because I'm gonna write path import pandas as PD. And then path equal to, where's my data? My data's here. CSV. Okay, so first of all, I'm gonna import the data, and then I'm gonna say data equal to PD dot read CSV. See, come on. Okay, path. And now I'm gonna have x equal to data dot job. I'm lazy. Please allow me directly use like this way. What's the name? Span question mark. Okay. I'm lazy to write the data dot column 0 like this. Spams. Spam or spams, I forgot. Spam, okay, question mark. Drop this one and y equal to data, spam. Okay, so now I have x and y, and I simply just need to, do, let's say, MMB class vacation, and then model equal to multinomial MB, and then again alpha equal to 1, or you can even ignore it because by default, come on, it doesn't show the hint, but by default alpha equal to 1, because here we required, here alpha equal to 1. Okay, and now I can write a model.fit x and y. Okay, now we have already had all this. But remember, consider consider this email. Congratulations, you win 1 million. So 100,000. Create account to claim your $100,000. Okay, is this one a spam email? Okay, so we need to, let's say, test our data. As we just mentioned, we are gonna have x test equal to 20011. Remember? Yeah, 20011. However, be careful in scikit-learn. It requires everything to be returned in a 2D array, even if you only have one test of data, because it just considers that you have many test of data. That's why, you know what I mean? And it requires you in the 2D. Okay, if you write a 1D, it will show you the error message. Okay, and then if let's say I can say if model, or let's say, let me just make my life easier. I don't print. This email is okay, then we're gonna say span 1, non-span 0. Then let me see, model dot predict x test. Let me see. Oh, okay. Similar to the 2D here, you need a 0. So this means you're gonna predict the 0th element, although it only has one, element, but here we go. Oh, how come? Let me see, span not founding access. What? I just saw it. Wait. How come it's not span? Okay, that means by default it's really by default is the row. Okay, x is equal to 1. Then I should okay, result is 1. 1 means that's a span. You see, so this is how we can make this, to work. And I believe there's I forgot the name. At that time when I remember I played it when I started this thing. In Kaggle, everybody knows Kaggle. Kaggle.com, let's say. So this is a website very famous for providing a lot of training data. I remember there was a group of data ready for training 5,000 or how many data of those kind of emails. And you can really run your own baby project here. Of course, nobody can come in terms of this, nobody can compete with Google because they have the biggest database. But we can still get some local database, and then they already marked in the training data, which is spam or not spam or something. And you can use this, and then you can just copy and paste to a real spam email. I believe everybody will receive tons of spam email every day, right? Different kind of things. Oh, here's your UPS package. Your UPS package is not arrived or something. And then pick up or something. Oh, you win some how much money or get the money, something like that. You can really use that data to train it. I believe you can train, let's say, spam email. I don't know whether I can find something. Okay, spam email detection. But what if in the database? Let me see. Filter by. I remember there was something like in the database. Anyway, where it is? Dataset. Yeah. Then from the dataset, you call spam email. You should be able to find a lot of. Let's say here. They should have a lot of different things here, but of course here I just use the naive bias. You have tons of methods to okay, word and cloud. You have tons of methods to load those things, and you can train. And you can just play a small project, and after training this, run in your local database to see how it works. Okay, so due to time limit, I'm not gonna expand too much here. Indeed, all of these kind of things can be a small project. Okay, and then finally, there's still one thing I want to mention. That's how we did. Again, be careful. You must make it a 2B 2D. I can show you what if you don't make it a 2B 2D. Suppose I make it just 1D. And of course, here I don't need a 0 anymore. And let me to show you an error. Show me error, but it's not expected to be the error here. Where that's line 15, where the thing. Oh, here. It will show error of other things. See it? If you read it, it's not shape -1, 1. In other words, it's kind of like you reshape the column because it should have like if your data has a single feature or something, contain a single sample, so that the truth is that you need to make it to be 2D. Expect a 2D array, got 1D array instead. You see what I mean? So that's the thing. I can just recover everything. Yeah. So if we make it like this way, then it's going to be correct. So that's the thing. Okay, the last thing I want to mention here for the multinomial here is that how do we get the feature data? Because here, of course, I mean, I'm a human. I know these data are these features, words like dollar, selected, link, account, win. I know these are sensitive kind of words, but consider long email or something, you cannot read it one by one, right? So a very popular thing is this. Since naive-based calculation is extremely simple and fast, I can just consider all the words appeared in my training data to be a feature. You may immediately argue, say, hey, it has so many features. How can we handle it? No worry, the computation cost is this. And usually m is a very small number, specifically in spam detection, m equal to 2. So you can ignore it as just constant in big O notation, which is the well, if you're not familiar with the computation complexity, you can just ignore it. You can just remember the conclusion is very simple, very fast. That's it. I mean, but it's a linear. So that even if I have a huge let's say number of features or huge number of training data, it doesn't matter. I can still calculate it very fast. You know what I mean? So we can indeed do like this way. And as far as I know, before like 2008 or 2000, which year, Google indeed, they are using the naive Bayes to automatically filter the feature of spam or not spam. One reason, because at that time, the neural network, the deep learning was not that popular at that time. It's not like nowadays, everything's neural network. Okay, that's everything about the naive Bayes. So far we have already introduced the two methods, which is the excuse me, let me drink some water. Which is the KNN and the naive Bayes. The next one I want to introduce is the logistic regression. So I know we spend a lot of time in linear regression because linear regression is the fundamental of everything. Once we go to the classifiers, it will be easier. And again, I still want to show some mathematics inside rather than purely coding. And I finally, what is naive Bayes? I don't know what is naive Bayes. I just know how you code. That's going to be something really wrong. Okay, so the next one is logistic regression. So logistic regression, it is directly, the idea is directly from actually linear regression. So that's why the reason it's called regression still, because it's from the linear regression. So the linear regression formula is this. By the way, here I use Cassie instead of using Y is because in this lecture, we will use Y to indicate the label a lot. I just don't want to make a confusion in the what notation. So temporarily, I use Cassie here. So I have the regression formula as Cassie equal to beta 0 plus beta tx. So again, for regression, our parameters are beta 0 and beta t, and the beta vector, right? And then technically, the range Cassie can be the whole R line, which is negative infinity to positive infinity. However, for classification, you cannot make it this way. For example, you tell me, oh, that result is a 1.5. What does that mean, 1.5? Can you say just something between, category 1 and category 2? Or you say if it's 1.2, that means it's category 1. Well, you will have a lot of mistakes if you make it like this way. It sounds interesting, but practically it doesn't work. So an idea is how can we kind of like use the traditional linear regression to do classification? How can we make it? One thing here is that almost all those kind of classification methods included in this course are generated from basic linear regression model, most of them. And then another thing is that, let me see here. I denote the realizations by X and Y. And here the C is just again a notation. We will use multi-nully, not multinomial. Although multi-nully is a simplified version of multinomial in which n equal to 1. I mean, trial is only one time in trial. But we will have this one for logistic regression. Let's directly come here to see the fundamental ideas of this one. So how can we convert, let's say, this kind of R line to a probability, or maybe kind of like convert a form of probability to a form of R line? How can we make it? One very simple method is this. We can replace this Kasi by the following function, which is log Qx and log Px. Qx, Px are two mass, PMF or PDF, density functions. Because, Px over Qx can be any number from 0 to infinity. And make it to be log, you know what I mean? It will immediately occupy the whole R line. Why? Because, what does a log function looks like? This is X, this is Y. The log function, this is 1. The log function, just looks like this way, right? This is a log function, log X, Y equal to log X. This is Y. It looks like this way. And hence, think about it. Since my P over Q is what any number between 0 and a positive infinity. And hence the log, it will occupy the whole R line. Hence, this one belongs to R. And the good thing is I involved two probability density or probability mass function, Qx and Px. So that's how we make it. Be careful, you cannot only make it to be Qx, Px over Qx. Why? Because Px over Qx, the domain is 0 to positive infinity. It does not include the negative infinity, does not include the something less than 0, the negative part. That's why we did log, okay? Okay, now the thing is, how would you figure out Px and Qx? I mean, you cannot just randomly, to make one. So the idea, the model of logistic regression, LGR, is this. So remember, we're doing classification, right? We have y equal to m classes, which is y equal to 1 to m. Okay, so I'm gonna use the last class to be a reference, and then for each other classes, I make it to be this way. So my Qx gonna be probability y equal to 1 given x, and my Px is this. My Px is this, and my Qx, I fix it to be the last class. And hence, you can see no matter, so let me write it here. So this is for C1. C1 means class 1, class 2, class m minus 1. And you can see I never use class m. Why? Because class m is here, always, used as a reference. So I created like this way. And let me see. And if I consider this one as something that we know, so we you just make it exponential, so there's no log. So here's gonna be exponential here, and then you're gonna have what? You're gonna move this one here, right? So I can have, for the jth class, I can have this one, which is pj equal to this. And you may say, what's the point? Well, the point is, don't forget that this is a probability distribution, meaning that the summation of j from 1 to m of this must be equal to 1. And hence, you see what I mean? I can immediately get something, which is I just sum all of them, it must be equal to 1. And since I have this representation, for all of them, I can just represent by this probability y equal to m and x equal to x. And hence, I immediately get this formula, which is the probability y equal to m given x equal to x equal to this part. So now I have already solved this part, and each probability, each class this is the prior, not the posterior. The prior is sorry, this is the posterior. This is given by a function of this, and I already get this one equal to this. So I can immediately write the function, the formula of probability y equal to j given x equal to x, right? So here we go. I immediately get this. A special case for the LGR model is m equal to 2, which is 2 classes, which is the most common classification problem, actually. Yes or no? And here we can get these two. The reason, it's so simplified simply because once I got this one, so y equal to simply 1 minus this. Why? Because this one plus this one must be equal to 1 because that's a PMF, right? So I use this one minus this one and get this one. So everything's extremely simple. Okay. Now, well, we have from the method of this, then how can we run the estimation? How can we get this beta, this E, everything? How can we get it? So in order to fit these parameters, we will apply the idea of multi-nully versus Bernoulli. It's like a Bernoulli distribution is a special case of the what? Special case of the multinomial distribution in which trial equal to 1. Similar thing, multi-nully distribution is a special case of multinomial distribution in which also in trial, the number of trial equal to 1. Here's some very brief introduction. So Bernoulli distribution is I have two outcomes again, success and failure, and I just run the experiment for one time, or I just make one trial, and the PMF is this. So I don't have the binomial coefficient, right? Okay, multi-nully, the same thing, but instead of two outcomes, success and failure, I have m outcomes. And since I only have one trial, again, remember let me just remember we just mentioned in the naive bias the multinomial distribution. Multinomial, here we go. Remember we have this, but since I only have one trial, one choose one is what, one choose one is what. So we no longer need this coefficient, and hence I can directly write this production part. So I directly get this thing. And then how can we, use this one to do the logistical regression? Okay, because let me see here. Okay, in each, be careful, each of the n training data, we have an m dimension label. So this m dimension label is the same as what I said x here, which is just a coding of, appearance of how many times. But here, whose elements of one denotes 1, 1 and m minus 1 zeros. So this means, okay, finally, which result? You know what I mean? Because here I have m results. It's not kind of like binomial, but Bernoulli, I only have 2 results. So you only need to have one, number, which is success. Is success, does success happen or not? If success happen, then happen. Otherwise, it not happen. But here we have because once I know success happened, then failure must be not happen, must, be the case which is not happen, but not occur. But here, since we have n features, unless you exactly know which one exactly happened, then all others not occurs. But this is gonna be kind of tedious. So in general, we can still use a vector in n dimension vector to indicate which one occurs and all others are 0. So for example, let's say suppose I have 3 outcomes. Outcome 2 occurs. So I can just write it to be like this way, which is 0, outcome 2 occurs, 1, 0. So in the whole vector, there must be only 1, 1, and all others are 0. So this is the meaning of here. Here, exactly, I showed the example. If we have 3 classes, the label I belong to class 2, so it's going to be this way. Okay, now let's see how can we model it. So if we already got the probability model for this one, suppose I know it, okay, suppose I know it. The truth is I don't know it. But suppose I know it, I can apply multinomial, the multi-nully distribution to LGR to fit the parameters, which is like this one. And remember, the PMF is this, which is nothing but a multiplication of everything. Okay, now I do multiplication of everything. So where do I get these things? It's from here. You see, it's from here. For m, y equal to m, because we use it as a reference, so I will discuss it independently as this form, while for y equal to j, j not equal to m, it is in this one. So I just plug in these 2 formulas here, and I get this, and plug into the binomial PMF. So I get this one, and then I will get the logarithm. Here I need to mention MLE. I know many of you have known MLE. Just a very, very quick mention. So the idea of MLE is to estimate the parameter by probability distribution. So if we consider this one, the vector x is a variable here, the likelihood is I consider these n samples, or let's say n training data, somewhat these means the density, or this means that like PMF, this is directly a probability. Density is a density, not a probability, but still a number, right? With a bigger density, that means higher chance. With a smaller density, lower chance. Probability, of course, the same. So I'm gonna multiply, the density function or multiply the PMF of all this n training data, and I will get a number, which is called a likelihood function. Then I need to tell, I need to figure out which theta should I use, the theta as a parameter, so that this likelihood, which means what I see, has the largest chance to occur. The philosophy or the principle behind the MLE is that we believe here that the samples we observed can be representative, and hence, since we did have seen it, it should have the largest chance to occur, to make it happen, and hence I want to figure out the theta that can maximize my likelihood, maximize the chance that it occurs. So this is the meaning of MLE. And in many cases, because of exponential, we make it log MLE, which is nothing, you just make a log. So multiplication becomes summation, make a log here. Then we have this one. We will calculate the log MLE of it. The details you can just check. Actually, super simple. Just you plug in the thing and then organize the items something. And here you need to have the important thing, which is for each training data, the feature exactly occurs one time. And then you will get this formula. So this is the log likelihood of the LGR. But this one, well, my parameters are the beta J0 and beta J. It's very difficult. How can I maximize it? There's no closed form, unfortunately. There are some iterative methods, especially for m equal to 2. There's a very, very fast method, which is, LRLS, which is actually Newton's method. I'm not sure whether you're familiar with Newton's method or not. If you're not, you can just click it, which is gradient-based method. Pretty simple. And then what? And then this is other works for equal to 2. But if there are more than 2 classes, that's gonna be a bit more difficult. There are many, many papers to write how to estimate it numerically. It can be long course, but here the good thing is scikit library includes built-in. There are several kind of solvers there, so we can directly solve it. Oh, sorry, I just realized that the time's here. So here's a summary. I will leave the summary to the next class. So this is everything about today's class. Thank you and have a good night. Bye-bye.